Have you ever wondered what gravitational waves are and why their discovery was so significant that it won the Nobel Prize in Physics? Let's dive into the world of gravitational waves, a concept that is as fascinating as it is complex. Picture the universe as a vast cosmic canvas. Within this canvas, everything with mass exerts a force known as gravity. Whether it's the moon pulling the tides or an apple falling from a tree, gravity is the invisible string that binds the universe together. But gravity isn't just a force, it's also a distortion of space and time, a concept introduced to us by the legendary physicist Albert Einstein. According to his theory of general relativity, massive objects like planets, stars, or even black holes warp the space around them, much like a bowling ball sitting on a trampoline would distort the fabric beneath it. Now, when these massive objects move, they cause ripples in this fabric, creating what we call gravitational waves. Imagine a spinning pair of neutron stars or black holes. As they whirl around each other at mind-boggling speeds, they create waves that stretch and squeeze space-time itself, propagating at the speed of light. These are gravitational waves, disturbances in the fabric of space and time. These waves are incredibly subtle and delicate. Their effect is so tiny that for a long time, scientists weren't even sure they could ever be detected. It's like trying to hear the softest whisper in the midst of a rock concert. But we'll dive into the detection of these elusive waves in the next scene. So, to sum it up, gravitational waves are like ripples spreading across a pond. But in this case, the pond is the fabric of space and time. They're the cosmic messengers that carry information about events billions of light years away, giving us a new way to study the universe and its most violent phenomena. Detecting these ripples in space-time is no easy task. Imagine trying to measure something so infinitesimally small that it's 1,000 times smaller than an atomic nucleus. That's the enormous challenge scientists faced when trying to detect gravitational waves. These waves, as proposed by Albert Einstein, distort space-time by an incredibly tiny amount. This distortion is equivalent to changing the distance to the nearest star outside of our solar system by the width of a human hair. It's like finding a needle in not just one, but countless haystacks. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, a marvel of human ingenuity and a testament to our relentless pursuit of understanding the universe. LIGO uses a method known as laser interferometry to measure these minute changes. Here's how it works. LIGO has two arms, each 4 kilometers long, arranged in an L shape. A laser beam is split into two and sent down each arm, where it bounces off mirrors and returns to the starting point. Now, if a gravitational wave passes through, it will slightly stretch one arm and compress the other. This tiny difference in length alters the path of the laser beams and creates an interference pattern that scientists can measure. But it's not as simple as it sounds. To make this detection, LIGO needs to be incredibly sensitive. It has to differentiate between a genuine signal from a gravitational wave and the countless sources of noise, like seismic activity or even a truck driving by. To overcome this, LIGO uses two observatories, one in Washington and the other in Louisiana. A genuine gravitational wave would be detected by both observatories with a slight delay between them due to the speed of light. This double-check system ensures the validity of the detection and filters out local disturbances. The breakthrough made by LIGO has opened up a new window into the universe. It allows us to listen to the symphony of cosmic events that were previously silent to us. So, through the ingenious design of LIGO, we now have an entirely new way to observe the universe. The detection of gravitational waves was a game-changing event in physics. This discovery, made in the second decade of the 21st century, confirmed a century-old prediction of Albert Einstein's general theory of relativity, first published in 1915. Einstein's theory painted a picture of the universe that was radically different from what had been thought before. He proposed that what we perceive as gravity is actually the warping of space and time by massive objects. Imagine a bowling ball on a trampoline, distorting the fabric beneath it. That's a simplified analogy of how mass distorts the fabric of space-time. Now, when massive objects accelerate, like when two black holes orbit each other, they produce ripples in this fabric, much like how a splashing fish creates ripples on a pond. These ripples, these distortions in space-time, are what we call gravitational waves. But why is this discovery so significant? Well, for starters, it confirmed that Einstein was right. His general theory of relativity passed yet another test. But the implications go beyond just proving Einstein correct. Gravitational waves give us a new way to observe the universe. Traditional astronomy relies on light and other forms of electromagnetic radiation. But not all cosmic events produce light. Black holes, for instance, are famously dark, but they do produce gravitational waves. So, with this new tool at our disposal, we can study events and objects that were previously invisible to us. In essence, the detection of gravitational waves has the potential to open up a whole new branch of astronomy. We can probe deeper into the universe and uncover secrets that have been hidden from us for billions of years. Who knows what we might find? The possibilities are, quite literally, astronomical. So, in conclusion, the detection of gravitational waves was not just a triumph of scientific endeavor. It was a moment that expanded our understanding of the cosmos. Gravitational waves have confirmed our theories about the universe and opened up new avenues for exploration. But why did this discovery earn the Nobel Prize in Physics, you may ask? Well, let's delve into the reasons. The discovery of gravitational waves was nothing short of a revolution in the field of physics. It confirmed a century-old prediction by Albert Einstein, providing a whole new way to observe the cosmos. Before this, our view of the universe was limited to electromagnetic waves such as light and radio waves. But gravitational waves, stretching and squeezing space itself, reveal hidden parts of the universe that were previously unobservable. The detection of these elusive waves required not just a brilliant concept, but also groundbreaking technological innovation. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is a marvel of engineering. It is sensitive enough to measure changes in distance less than 1,000th the diameter of a proton. That's a particle so tiny that 1 million lined up would be about the size of a grain of sand. It's like being able to detect a hair's breadth change in the distance between the Earth and the nearest star, Proxima Centauri. But LIGO is not just a technological triumph. It's also the result of decades of dedicated work by a team of researchers across the globe. The path to this discovery was filled with obstacles and setbacks. The scientists had to convince skeptics, secure funding, and overcome countless technical challenges. But they never gave up. Their perseverance and innovation are a shining example of what humans can achieve when they push the boundaries of knowledge and technology. This discovery opened a new window into the universe, ushering in the era of gravitational wave astronomy. It has already led to remarkable insights, such as the observation of colliding neutron stars, and promises to reveal even more cosmic secrets in the future. The Nobel Prize was a recognition of this monumental achievement, a true testament to human ingenuity and perseverance. The discovery of gravitational waves has opened up a new era in astronomy. This breakthrough has shifted our perspective, giving us a fresh lens through which we can study the cosmos. The potential applications of gravitational wave detection are as vast as the universe itself. Imagine peering into the darkest corners of the universe, observing black holes not just as abstract concepts, but as tangible, measurable entities. Or diving deeper into neutron stars, these incredibly dense remnants of supernovae, and unraveling the mysteries they hold. But why stop there? Gravitational waves might even allow us to probe the very origins of the universe, the Big Bang itself. This could provide us with a more complete and comprehensive understanding of how our universe came to be and how it continues to evolve. The discovery of gravitational waves has truly revolutionized our understanding of the universe. And who knows what we'll discover next.